Good afternoon, everyone. My name is Mudit. I'm a final year student at University of Zurich with Lucio Meyer. And today I'm going to discuss about the nature of the environment or nature of the mechanism which solves the final parsec problem so that we can see all these amazing LISA merger of massive black hole binary by LISA. So all the work I'm going to show today is done with these wonderful collaborators, and most of them are in audience or online. So galaxies co-evolve with their central black hole. This is something we know, but the exact mechanism is something which is a hot research topic. These massive black holes manifest themselves mainly via active galactic nuclei or some other high-energy phenomena such as tidal reception event. If we can infer the AGN's bolometric luminosity, we can approximately infer the mass and also how much gas is accreting in terms of Eddington ratio, F Eddington, which should be at most 1 in case of hydrostatic equilibrium, but there is a mechanism to go beyond it. So when galaxies merge, then dynamic friction against dark matter, star, or gas can bring the two black holes to the center of a newly formed galaxy and make a bound pair. That is what we call MBHB. However, beyond that, there is a problem because the enclosed orbital mass is comparable to the secondary. So dynamic friction is inefficient. And at that point, two-body relation time is also longer than Hubble time. So how do we go beyond this stage? So in the last decade or so, it has been argued that we need some kind of environment. That environment is mainly either gas-rich or it has a triaxial stellar potential. That means stars can come and go in an eccentric orbit, take away angular momentum, and go away. I'm going to focus on gas because that is a more efficient channel which can lead to many mergers. So if gas is relatively efficient, then it can settle into a coplanar geometrically thin disk. And this model can explain a lot of properties of observed AGN. However, gaps remain like emission variability or spectral signature. So just to show you a case, if the aspect ratio of the disk is like 0.1 or something, then you have something like this in which the binary mass ratio when it's less than 25, primary to secondary. The binary vacates all the gas around it. However, streams of gas still flow into the cavity and make mini disk, and you have this kind of scenario. However, another scenario is that when the aspect ratio is higher than that or is lower than that and closer to maybe more reality because the observed AGNs have aspect ratio of 0.01. Then in those cases, you do not have mini disk. However, there are still streams of gas which are flowing in, and the binary is torquing the system. So both simulations are done with concurrent gravitational wave at 50 social radius using Gizmo. So now the question is, once the gas is able to bring the binary to milliparsec, gravitational wave becomes strong enough to quickly drive them to merger. And these are things which we'll see in LISA. And LISA will have many science cases, but for MBHBs, let me mention 3 of them. First of all, LISA will see black hole binaries up to redshift 20 in principle. Whether they exist or not, that's up to observations. But that means we can constrain the MBH mass function with better certainty. LISA will localize the source of the MBHB to 0.01 degree to 10 degrees squared, depending on orbital separation and how close the source is to us. And that means it's very good for electromagnetic counterpart study. And the last part is MBHBs can spend up to a few years in spiral in the band. That means a lot of cycles. And that could allow us to measure beyond vacuum circular signals with better certainty than what LVK can do right now. If LISA is evolving from redshift 1 and we have at parsec scale uniformly distributed eccentricity and spin, then depending on whether it's a prograde channel or retrograde channel, we did the study in which we say that 1 year of merger. In prograde, the effective spin will be almost 1. While in retrograde, the spin will be more distributed because retrograde accretion or retrograde leads to faster in spiral. And orbital eccentricity in prograde also will be lower, like 10 to the minus 2.75, depending on accretion rate. And in retrograde will be a bit higher, and it will depend on the resonances. So all these things I'm going to show in this talk. You can always discuss with me later, but I'm going to just show teaser. Another mechanism apart from eccentricity and spin, which can tell us about environment, is the dephasing or how much gas is torquing the binary. So there have been a lot of studies in the literature in the last decade or so which have studied how the gas torque the binary. However, because of computational limitation or some other science case, they are mostly two-dimensional with fixed Newtonian orbit. That means they fix the binary and then they let the gas evolve and they measure torque from that. And also, so basically they are mostly applicable for sub-parsec scale and where the gravitational waves are not so important. But still, these are the studies we had and we use them. So what I argued in my first paper is that we can encompass these studies in a framework in which we measure the gas torque in terms of this viscous torque or a viscous driven accretion torque, which is m dot a square omega. A is semi-major axis and omega is the angular frequency, so that we can analytically model how the gas is changing semi-major axis. And here in this formula, you can see that A dot gas is a function of Z, which is coming from simulation. Q is the mass ratio. F at intent is the observation inferred value. And epsilon is the relative efficiency, which is typically 0.1. So if Z is positive, that means it's slowing down the inspiral. And if Z is negative, then it's speeding up the inspiral. So once you have that, you can add A dot gas as a perturbation to A dot GW. And there is no cross term because these simulations are not done with gravitational wave. However, you can argue that A dot gas is so smaller than A dot GW, maybe the cross term is not important. And there's an asterisk which I will discuss just in a bit. So with this framework, we can encompass secular effect like migration and accretion. However, there have been studies which study suborbital high frequency fluctuations or disk-induced precession. There is an asterisk because last month we put out this work in which we were able to do the simulation with gravitational wave as the simulation I showed in the initial slides. And this simulation is done with the 3-dimensional live orbit post-Newtonian things. And apart from measuring the Z value of -36, we are also able to report a cross term. Its exact functional form is unknown, but we propose that it should be like simple multiplication of 2 terms. So just to give you the intuition, when the binary is evolving under gravitational wave, and there is a gas disk around it, so as the binary is evolving further and further, there is in the waveform, it will be seen like a dephasing, in which you can see that the orange dashed line is left behind, and the blue one is the vacuum one. At this point, what most people do is that they just calculate the cumulative dephasing from the initial observation to the final observation, which is the first good first step. However, dephasing has a problem because it can be mimicked by many processes. So my collaborators and I thought about how to go beyond this thing. And what we did is that instead of having dephasing as a cumulative number, we model it as a frequency dependent function. And it comes out around -4p in relative order. You can see that it depends on frequency of the gravitational wave, but also in this Z and F at intent, and they come in a combination. It's very hard to measure them separately. So we also wanted to have better waveforms, and because we are considering gas dephasing and eccentricity both, and so basically the inspiral waveforms are good enough for our kind of study. And we have a waveform like 3.5 relative Pn order, which is good enough for aligned spin and eccentricity of 0.1. And as the gas will also align the black hole, so maybe it's good, but of course, we can always go do better than this. We employ LISA beta software developed by Marseille et al., which consider LISA response, like how the LISA will be in motion, and we have to also do time delay interferometry to mitigate overwhelming laser noise. And in the end, we want to use Bayesian inference because we want to vary all the parameter mass-mass ratio, spins, time of coalescence, so that we can confidently say we have detected something. So just to give you an example, if you're varying your mass, so 10 to the 5 solar mass, mass ratio 8, both spins 0.9 and time of coalescence of 4 years at redshift 1, then in vacuum, at best you can measure initial eccentricity of 10 to the minus 2.75. And in gas, because now you have a competing effect, which is also decaying as the go close to merger, you have to go a bit higher, but at least it is showing that for some part of the parameter space, you should be able to measure gas excited eccentricities. If you assume some value of Z, then for circular system, you can measure F at intent of like 0.1. And for eccentric system, you can measure F at intent of 1. So that means you are able to put some constraint on gas disk properties using only gravitational wave. However, there are, of course, degeneracies. So if you have your favorite system, you can always look up the paper and find that for your favorite system, how well you can measure eccentricity and gas in different scenarios. So just to conclude, the minimum eccentricity we can measure using for MBHBs using LISA is this. That means for for some parameter space, it's gas excited should be possible. The minimum measure intent ratio is a 0.1 for circular and 1 for eccentric. That means you can put some constraint using gravitational wave. And if you have electromagnetic counterpart of population synthesis, that will just make things even better. For the first time, and this is also something I didn't discuss in detail, but you can discuss with me, is that for the first time we are able to give measurement of gas torque MBHB in the LISA band, which was not done before. And we also provide estimate of a novel GW gas coupling that can improve the inference of how the population at parsec scale is related to the population in LISA band. And one thing I didn't have time to discuss because the meeting is more for astrophysics is that if you ignore this F at intent of 0.1 or eccentricity of 10 to the minus 2.5 in a realistic data analysis setup, then you can cause false violation of GR, which is of course something you want to avoid. Because if you are able to cause false violation of GR with something which is astrophysical, then you can mask or mimic something in the early universe if there is an actual deviation from GR. So that is something which is also important to keep in mind. So just to conclude, we want to improve both astrophysical as well as waveform modeling if we want to understand massive black hole binary evolution in the LISA era. Thank you.